Hey everyone, it's Andrew Brown, and welcome to the Free GenAI Bootcamp. We are here with both Rob and Kemalcan, and we got a really cool project to showcase to you here. But before we look at that project, I'd like Rob and Kemalcan to introduce themselves to our boot campers. So Rob, you want to start?
Yeah, hello everybody. I'm Rob Koch. I work for Slalom Consulting as a data engineer principal. I'm here today having worked here for 2.5 years, doing tech consulting for mostly data and machine learning projects. I live in the Seattle, Washington area. And it's great to be here. Thank you for inviting us to have a visitor instruction, and myself and Kemalcan. So I'm going to explain a little bit about what we're doing, and then I'll pass it over to him. But I am also a AWS data hero, familiar space there with Andrew Brown as well. So thanks for being here, and I'll let Kemalcan introduce himself.
Hello, everybody. My name is Kemalcan. I'm a senior engineer at Slalom as well, working with Rob here. I'm very excited to be a part of Free GenAI Bootcamp today. And I think we can start with the technical explanations now. Rob, back to
you. Great. So I came into this kind of naive, so to speak. I mean, it really could, with machine learning and technology, it's quite exciting to be able to play around with and to be able, to either hit a wall or maybe run into some frustrating things. But that's part of what we're doing here is we're going to walk you through a bit of our journey of how we've gotten to the point where we have with computer to recognize sign language. Some interesting things that we found along the way. Different points that we found that were quite interesting, roadblocks and things like what we did to overcome some of those. We're not quite 100% there yet, but we do have, there are other companies out there that are professionally running this type of activity, and their work is far beyond what we have done here on the side. But I will say that the point is it's a journey, and it's fun, and it's challenging, and it's been really cool to engage with the community and all of that. So that's really why we're here. So just wanted to set up a little bit of the background, the coding and the framework and what we've used over and over for other things, not only sign language, but could possibly be used for gesture-based computing and things like that. What we're using here could be used for that, as well as, communicating, like telling your computer what to do, for an example. So the motivations are not only for sign language recognition, but also, not only translation purposes, but really a lot of other things that are gesture-based. We started out working with, first, I came to Kemalcan with an idea of saying, hey, I wanted to do sign language recognition, right? And so everybody was excited to participate in the journey. So I guess you could explain maybe the first thing you did. What did you ask for at the very beginning of how to get this going?
I did have a very limited knowledge about American Sign Language letters, alphabets. First thing I asked if every single letter has an expression in American Sign Language. And I asked if any of them they require multiple movements rather than one static image. Eventually, I knew we were going to deal with videos, but I approached this as frames or pictures rather than video. So that's why it was important to understand. And it turned out that letters, for example, J and Z, are represented in multiple movements rather than one static image, while the rest of the 24 letters are represented with one static image. And of course, to understand the area domain, I asked many more questions, but we immediately dived in. Like we wanted to create something fast and fail fast, and then move forward. That was the initial goal.
Yeah, absolutely. And one of the first things that Kemalcan did was ask me for some videos. So we needed to train the data, and as well as needing the data that we could label, right?
Correct.
So we did a little bit of a training of the data. We needed that data then to help us progress the data that we could train and test as well. So we had reached out to some wonderful people at CNCF, the Cloud Native Computing Foundation, and the Deaf of Hard and Hearing Working Group there. I asked several of those members if they wouldn't mind sending me some videos of them. And thank you to all of you who did send me some videos. I just asked everyone to sign the alphabet A to Z. And so I collected all of those videos from various people in various environments, and then handed them to Kemalcan to be able to work with them. And then, yeah, what happened after? What did you do with those videos that I gave to you?
So we were first of all very lucky to have these videos because they were real videos rather than toy data sets. Yet we needed more data. So first we started with these videos. We chopped them up and shuffled them into multiple letters. Another thing we needed to do was to create augmentations. So one image, for example, L can be represented like this. However, it can be like this or this. So taking one image, rotating it, flipping it, changing the colors, and apply something called chromatic aberrations, or changing the structure of it, basically, was essential because this helped us to create multiple images from one image.
Mm-hmm.
And that was our starting point. Once we felt like this is good enough to apply it on a model, we started laying out the pipeline process and apply different models and experiment different models. That was the initial phase. If that's okay, I can continue.
Please, yeah, feel free to. So you tried different models and then created what we found was to be a good one, right? And then those models were able to get the shape of the hand. So it was looking at things like something around the shape of the hand, or did you use anything specific to help that out other than the things you've already mentioned? I know some of the challenges that we had with the data sets were that the volume and all of that, just the sheer volume of that particular sign. Like, I mean, there's not a whole lot of it out there and readily available. So that was kind of some of the challenges we faced, right?
The sheer volume of video data the data set that you had?
Yes, very correct. So that volume, there were maybe like 10 videos. The amount of data was not enough, so we needed to supplement these with the data we found online. We found free data sets online.
Okay.
We shoveled everything. Initially, I wanted to use those videos as a test data set, and then I shuffled everything, tried different approaches, but first models failed, and luckily failed fast. They were not great at in inference side. So we thought that must be mostly because of the number of data in the data sets. We had in total we had 4,000 images for the entire 26 categories labels in the alphabet, and that was not enough. Simultaneously, we looked for bigger data sets and different approaches. We started thinking about what we can do. And finally, we found another data set that had augmented data in it. In other words, one image can be represented in multiple ways, as much as the lower quality, higher quality, etc.
The so like lots of variations of that data there. I guess the original reason was you wanted to see what you could do at the bare minimum with your own data set, and then after that was not enough, that's why you had to reach out to get more.
Correct. Yes.
Okay.
What we tried with our data set was not good enough. In some cases, some of the letters were not even recognized. They were not detected. So we knew we need more data. We need more data, and we need diverse data.
Okay. Sorry. So when you gave the original data set, like you did not realize the diversity of data you needed during instruction, or it was just the data that you got back was the data that you got back from your original data collection?
This is what we had on the hand in the beginning. We had our data was diverse enough, but apparently we needed more. So that's why we try to find bigger, better data sets.
The original data set was in a video format, right? And so these other data sets, were they in video or were they just images? And did you have to convert the original videos into images to normalize the data set?
Yes. Each video has frame per second number. Based on that number, we extracted images, frames from those videos and used them. And then, of course, there's like a whole pipeline. We augmented them and normalized them, resize, etc. This is that was the first few experiments. Once we felt like, okay, we have enough data sets, which is about 7,000 images per letter.
Mm-hmm.
It's quite a bit. Okay, we said this is good enough. Let's find out different approach, different paths to increase the accuracy and continue. One of the we were lucky to find this open source library called MediaPipe. MediaPipe is from Google. They developed it. There are multiple versions of it, but one version extracts the hand image from any images, recognizes it, and gives 21 points in a hand. For each point, it gives X, Y, and Z points, like data points, let's say. So therefore, we have, for one hand, we have 21 times 3, 63 data points.
For those points in the hands, do they correspond to bones or any physical structure, or it was more just like the mesh, the shape that they could provide?
Yeah, that's a great question. My understanding, they're not explicit about that. I can actually show the.
That'd be cool to see. Yeah.
So remember also that the ASL, American Sign Language, is a spatial language, and it relies on the space around it, right? So when we're signing, you're dealing with a lot of background noise, so to speak. Like, I've got this shirt on that you could consider noisy versus the white wall behind me is not. So if I sign A here, half of my hand is on the wall and the other half of my hand is on my shirt for the background. Oh. So there's a lot of media libraries that struggle a lot with that particular scenario. Learning how to identify within the box where the hand is. If the wall is the same color as my hand, that would also be very hard for the computer to recognize. So luckily, we had a library available that was called MediaPipe, like Kemalcan just brought up here on the screen. There's some other open source versions called RTM Pose as well. We haven't experimented with that here, but we just chased down the low-hanging fruit to be able to use this library here. And you're able to see with the hands and how it can detect all of the different points there on the hand. So MediaPipe helped a lot with that. Was augmentation. Is that the correct word, that I'm using that correctly? So augmenting your hand shape to be able to find the various lines on it. So that worked out really well.
Yes. As you can see, there are 5 data points for, or let's say 5 points, not data point, 5 points for each finger, plus 1 at the bottom of the palm. So therefore, there are 21 points, and for each point, there is X, Y, and Z coordinates. So we use like in this phase, we call it feature. We call it feature extractions, feature engineering. Sort of it is. We didn't need to deal with the frame data anymore and those huge matrices. We only have features from each image. In those cases, in some cases, there are multiple hands in the image. Therefore, we have multiple those arrays for each image. And the rest is actually pure machine learning. Once we have the huge data sets, of course, we saved it in certain format and then not dealt with the images anymore. From that moment, we applied boosting methods and bagging methods like random forest. We used XGBoost, and as well as I mentioned, deep learning model Torch. We had some discussions, like some friends suggested that we need to stick with random forest because there is no pattern here. But I thought our features are great for Torch model. However, I was wrong. In the first experiments, again, Torch model did not give us great, not even good results, because, as I said, there's X, Y, and Z points for each point, those coordinates. Z coordinates did not give us a meaningful information. It didn't give us signal. It was pure noise, because Z, as you can imagine, dealt with the depth of the picture, and we didn't have a spatial data in that case. In other words, none of the picture, for example, this is a camera, let's say, and I am doing B, none of the pictures were taken from multiple spatial area of the hand. Therefore, that Z was irrelevant.
So it seems like it's like a 2-part problem, because I think Rob mentioned this earlier, but what's really important is that the source images, if you take a step back, have to be in the environment, and they have to be detected that way, because that's what's going to be what the web camera looks like. I had a question in the back of my head, which was, what would you like? Why didn't you think, or not why didn't you, but did you consider using synthetic data, meaning a 3D model of hands instead of having to get real images, 3D models in all the poses that you needed them in? But as Rob pointed out, was that you need it in a real environment, because what if your hand's up and your hand's real white and the background's real white and part of it is obscured? And we see MediaPipe, which is drawing these positions and lines. I'm assuming that we have those data points, like it's calculating, saying this data point is most likely this place in space. Is there any other means to detect a hand, or is this basically the natural way to possibly solve this problem? Like, I know there's ones where they literally look at the pixels, right, and they're doing some kind of detection of it, like computer vision. And but I guess my thought is like, was there any alternative besides these sticks or these vertices, or this really is the way to go? Sorry.
Yeah, that's a great question. Please go ahead.
So, yeah.
So with the manual hand shape, we are letting the machine decide which shape it is, right? And it had a lot of struggle with that at the beginning. For example, like if you were spelling A like this and then T like this,
Mm-hmm.
the thumb there comes in between the two fingers. And then you have S right here, right? So AT and S almost have a very similar hand shape. So that we noticed that was a challenge for the machine learning library, where if you had without media pipe to help it denote and identify those obvious differences, where is my thumb, right? Where is my thumb relative to my hand?
M and N would probably be very hard, right? Without media pipe. How does media pipe handle M and M well, or does that also have some challenges because they're so similar?
So with MediaPipe, that does all of the hard work, so to speak. So it's already, have years of programming, and they already have all of that incorporated into their library, where it makes it easier for us to then train the model, because it's looking at each one of these points on the hands, right? The 21 points like Kemalcan mentioned. And so it's identifying those different points and putting them into the model and training the data set on that. And now we have to rely on the source of the data without being able to, restore it to, 100 million images, right? We can use MediaPipe. It's a sort of, would you say it's a shortcut? I don't know if it's necessarily the best way to describe it, but maybe kind of like a shortcut.
Yes, it's a shortcut. We definitely outsourced that portion of the problem to MediaPipe. And once we have the feature, we didn't actually want to spend more time on detecting the hands. But in some pictures, MediaPipe couldn't detect the hands, even though there were hands. They were rare. We just didn't include them in our data sets. We saved them somewhere to check out to look for different patterns. This is still some work to do if we need to pursue like why MediaPipe failed to detect hands there. We saved those images, but we didn't spend time to investigate and work on it and optimize it.
I guess there's probably. Oh, sorry. I guess there's probably like a good enough approach, because if you have streaming video, right, and your hand is moving, it's not like you need to detect 100% of that there. And so, like, what was the like? I don't know, but what, like, how do you know like what the final thing is? Because it's always just calculating on the fly, right? So it's a very high chance that you will get it correct. So you only need to get a percentage correct. So yes.
Correct. There are percentages in two places. First, when we set up the media pipe, there's a percentage. If you are 30% sure, detect the hand. If not that. Like, you can change that percentage. Second percentage, of course, you can apply it on the machine learning model with the probability. Once we apply the machine learning model, as you are going to see in the demo, let's say WE, I will say welcome, WE, and these changes, hand moves, but model detects every single frame very fast.
Mm-hmm.
So it actually detects different letters between W and E. This is a post-processing problem, and we dealt with it in a different way. So far, I explained everything to the model. So we train the model, use PyTorch, and I say, okay, let's have some inference and see what it feels like that now. With the 3 points X, Y, Z coordinates, it didn't work well. But when we used X, Y only, it worked perfectly. Not perfectly, but it worked great.
Good enough, right? Yeah.
Yeah. They are not seeing it. I can go. So basically,
So yeah, one of the other things is there was a lot of math involved, or a lot of post-processing, like Kemalcan was talking about just now, with the finger spelling of W to E. It would capture every frame per second. So, I mean, that is a lot of frames, right? So we're talking about 24 to 30 frames per second, depending on your camera. And so the W, as you're making the transition between the W and the E and those letters, MediaPipe and our model would then wrongly identify the letters there. And so we would say something like, oh, we haven't told you the letter yet. And so W going to the E and picking up coming up with another letter. It's trying to find that, O or B or whatever it thinks it is in between during the transition time, even though it's short. So we were trying to figure out how to identify which is the right one and which one to keep. So that's kind of where the post-processing challenge comes in. And so Kemalcan will walk us through that.
Okay. Before we just jump into that, so the thing is that you have media pipelines producing these vertices of the spatial position of these things, right? And then you have to take that data and pipe it into something, and that's making a prediction of what it is. I'm guessing that prediction model is the model that you built, and it has a confidence score. So I guess maybe the confidence, like, does it produce a confidence score, and does that play into how you weight whether it is a letter or not, or do you look at past or prior frames that are close together to better determine it? And maybe I'm getting ahead of myself, but you're going to explain all this. But that's what I'm thinking in my head. So, but I'll let you go. Let you go at your pace here. Sorry.
This is a great point. Yeah, you mentioned like looking at the previous frame or not. That was our solution. But before when we get there, yes, for every single prediction, there's probability score. We initially tried to use it. One of the things that we tried was we said most probable letter, let's say W, and its percentage is like 40%. Second probable letter, let's say S, or let's say U, right? Let's say 20%. We try to apply a threshold. We said if there is like, if the first one is 2 times bigger than the other one, second one, give us the estimation. If not, don't give us any estimation. We tried different approaches like that, but unfortunately, none of the approaches which use the probability solved our problem. Okay. Our problem was number of frames and how fast the model was predicting, because hands change. We are not static images, right? We just like W-E, as I'm moving my hands, there are like 5 different letters between. But once we agreed with the model, we were satisfied with it. We thought we can solve this in the post-processing. And just like you said, looking at the previous frames was a great idea. What we did was, as you can see on the screen right now, for each frame, let's say one video, 30 seconds video has 900 frames. Let's say 30 frames per second is 900 frames. For each frame, we made an estimation. We started with W. Let's say we are going to spell welcome. W, and maybe W 20 times. And it's supposed to go to E, the next letter, but there is like B in the middle and there's S in the middle. There are different letters.
Sorry, just a quick question. Does this app go beyond just detecting letters, and it will actually detect words?
This is what our goal is.
Okay, because like I haven't seen like maybe Rob knows what I'm talking about, but like I've gone
That's
to
a
conferences.
discussion for another day for sure.
Okay.
We definitely are trying to do the models and things like that where,
Okay.
it's static images and things like that. And having many sign languages can recognize, but there's a lot of moving parts, right? So we're, if you're driving this way and you're moving forward, or you're going somewhere and you're literally coming from here to there in that movement. Here where we're, the letters are, and more of the static where it's literally in one place, right? But we did run into some issues with the two letters next to each other that involve movement. So that's something that we are, we'll tackle that on another day, right?
Well,
So it's just,
I was gonna say if you solved it, because it's hard. Like I can just think of all the moving parts, but I've seen a lot of demos of detecting static images, like literally like frame, like old timey photos where you had to stand really still. It's like stand really still, show us the letter you have, and it'll detect that, right? And so now we're at step 2, where it's like, okay, we can detect it in motion, and now step 3, it's like, let's get a word. If we get a word, that'd be really cool. Be able to spell the word. Sorry, yes. Mm-hmm. It's hard. Yeah, it's hard.
yeah. So I was just thinking you can explain maybe how we did that post-processing part.
Yeah, for the post-process part, we, as I said, for each frame, we had the estimation prediction, and we looked where that prediction changes, and we dropped every single letter that was not predicted less than 10 times, because clearly they are intermissionary letters, like they are like hands are changing between letters. This is what was happening. So we dropped those. This is how we solve the problem.
So if I sign W like this, and you can see that this is a W, and have you seen the percentages of what that comes in? Like if you were to sign W, like maybe you sign it like this or like this, is that a lower probability that it's going to detect a W, right? Because it's like leaning forward versus like the coming up in between, or lowering down to the E. So if it was a W, what percentage do you see in your model just straight up like this?
It's hard to answer. Like each letter, of course, model, when it does prediction, it doesn't actually give one prediction. It gives 26 predictions and gives a probability for each of these 26 predictions. And we first
just to help the boot campers there. 26 because there's 26 letters, and so there's a confidence score of whatever. So you might have a letter like M and N, and they both might have both high confidence scores because they're so darn similar. And then you have ones that are like maybe A might be closer, and other ones. Sorry, yes.
Yes, correct. For model spits out confidence score or probability for each of the labels, and actually return us all labels with the associated probability. But what we call prediction is the highest probability, right? So yeah, back to your question, we can actually see the confidence score of each label. Yeah.
So imagine you have something that's culture, like I have 10,000 letters, let's say, in another alphabet. Would then that have to learn? Could the model handle learning all of that? Like if you were to try to come up with a probability score for each of the 10,000 letters in an alphabet, let's say, if that were the case, and would it get too much pressure on the model, or once you train it, it would be fine?
You probably need a bigger architecture for it. Yes. In fact, I'm talking about for deep learning models. you don't even need to train the model, because when you create the model with enough nodes, it associates random weights for each node, and it's ready to predict. It doesn't need to be trained. It doesn't need to be trained.
One other thought I was thinking about is that, you know, you have a letter, you like a confidence of what it is, but there is the shape of a letter on its way to be created. And so it'd be interesting if there was data on that, but I imagine that's hard because when you are morphing from one sign to another, how would you ever know where the hand is, right? So it's just like you can't even really have that kind of transition period because you have to know from which sign you're coming from to another sign. I'm just saying, like, if you had like a confidence story that this person is starting to form the letter W, right? And this is at the intermediate stage, how would you know? Because it's based on the shape of where the position of the hand was prior to the prior sign. But again, maybe we're getting too far in the weeds and too advanced. But when I think of LLMs, right, and they talk about predicting things, they talk about the whole sentence of the context. They look back and forward, the words, like they understand the context of it. And I thought, well, maybe if you have, you know, each frame is showing a representation, just like you feed into, I'm not saying we're doing an LLM, but you feed the data into there, each frame, and it kind of figures out the context. But I could see how that'd be really, really hard for Sign to build a model like that, right? So
very true. That's the reason why using this smoothing process and looking the previous and next letters is very important. So of course we cannot, even though we know the previous letter, we cannot know how you change the hand. For example, W to E, I can drop my, you know, first couple fingers first, or maybe last couple fingers first. You can't know that. But once you have like W 20 times, you're sure that this is a W. And once you see E 20 times or 30 times, you're sure that, okay, this person is representing E. Yeah, that's how we overcome. And this is automatically tying to a word, right? Like you have to look at the previous frame and next frame to make sure what letter it is. And also, if you're sure about this letter and if you're looking at the previous one and the next one, you are pretty much a rough idea about what the word is, which I will not give spoiler about that. It's the next phase.
do you think there's enough data out there for folks to develop these models to make them better, or is there still a lack of good ASL data, at least on your outings to find data?
Would you like to take that?
Yeah, so with the static images that we have there, using those tools like MediaPipe or RTM Pose and those type of things definitely help with getting the process more accelerated. And the ASL dictionaries that are out there, there's also a company out there that's making an effort to collect and harvest that kind of data. And so being able to have that access to that data and, you know, maybe could be sold and or given away to, you know, public use where they could enhance their models with that. With sign language, there's a lot of movement, as we've been talking about, and there's a lot of pixels, I guess, or points that you'd want to, if you can imagine MediaPipe, for example, doing all of those different points, we would need the library to give us all of this XYZ and spatial information that would give it better context as to what the sign is doing and where it's going and all of those things. For example, like if I am envisioning, you know, in kind of under a surface, like an underground, and then a tree was coming up over here. It can get that, you know, obviously it's demonstrating the roots of the tree kind of going in and then the tree growing up out of the ground, right? So there's a lot of nuances. That's where ASL will take a very long time. And I think it's a long way from being detected. I think that machine learning or the different professional companies like I was talking about earlier that are out there, and they get more of those signs exact English type recognition, where you would do the root and then sign the roots and then the tree. But that's not ASL. It's more of a visual spatial language, right? So I would sign it like roots going into a tree, like I just did. So the movement would definitely help identify what the person is saying. But we still have a long, long way to go as far as that's concerned. And how people sign are completely different too, even regionally within America. So it's like how people have different accents, like in Canada, you have an accent different than we do here in the States. And, people learn differently as well. And so there's regional signs that are specific to a specific region, right? So there's a lot of challenges that we have in sign language. I do recognize, yes, when we have speech to text, you can see that, that's pretty common out there in computer and web-based platforms and things, video chats, whatever that may be. And they, years and years and years of training, 30 plus years of training that those have, they started way back with companies like Dragon Speak and things like that have all of those data, right? Those companies, some of them are no longer around, but because of all of that data, before most of you were born, most likely, we've been collecting that data as a head start, right? And so sign language data and detection is in its infancy, really. So we've got a long way to go.
There's I think I've seen it. I'm not sure if you've seen it, Rob, but I'm assuming the domain, the problem is different from being able to make a model that can recognize sign. But I've seen these agents where it generates a fake person and they're signing. And so my question is, like, that person that is like, just how we have videos that make fake looking people. There's videos.
Yeah, like an avatar. An avatar. Yeah.
Are those signs even accurate? Like, do they actually do it? Is it like just a canned model? Like, and
some are, some are. I mean, I would say some companies out there have a really amazing job that they've done with making more realistic. Some of them are a little more cartoony than others, and some are, almost like a real person, like you've seen with AI, like diffusion and things like that, right? And different types of ones that have been improved to a point where we can now see it very realistic. So those avatars are kind of the same way, pretty easy to make them look that way. It's, and you could get there if they aren't, but yeah.
But I guess my core of my question is, like, just because they can generate one that looks like it's signing or maybe makes accurate signs, it's not the same thing as interpreting signs. And these are two different domain problems that have to be solved, right? So if one solved doesn't lend to the other, right? Or no?
Right.
Or I don't know.
So we have sign language interpreters that give a lot of the added context, like they can capture the emotions of the person and be able to interpret that, or if the person has an accent, or if the speech to text, that doesn't do a great job necessarily. Interpreters can interpret the facial expression that say, like, hey, I think this person didn't quite understand the question, or maybe it was hard to hear this particular nuance of that and it's not showing up in the text. So there's a lot of visual cues that interpreters can add value there. Hearing people, like maybe a person is not making sense or things are kind of vague, your face would shift to being like, I'm not quite understanding, right? Avatars are more kind of deadpan. They are operating off of assumptions maybe, or they might say the wrong thing, or where the interpreter would be like, actually, I don't think that's what they said, or that's what they meant, right? That's the interpreters that might fingerspell a word. That a lot of this happens in the tech world, right? We have to fingerspell a lot of things, and sometimes it gets spelled wrong. Then I can give the interpreter, I can feed that information back to them and say, this is actually the right way it's spelled. So yeah, with signs and being able to contribute that information back to each other working. So right, I'm sitting here and I'm taking in what the interpreter is signing, and there's a few times that over this, recording that we've gone back and forth and got some clarification there and things like that. So that kind of stuff happens that wouldn't necessarily happen within Avatar. So yeah, and then I guess if we're ready and there's no other questions, we can fall into a little bit more of the tech part.
Yeah, let's jump into the code or demo too.
Yeah, let's do that. So as I said, we are working on an application, but today I will be showing you Jupyter Notebook, and I'm hoping all of the boot campers are familiar with Jupyter Notebook and all of that. That's safe to assume, right?
Oh yeah, we covered in the Gen Essentials. They're all ready for Jupyter. Yep.
Okay.
Mm-hmm.
Do you want me to walk through the code a little bit, or just directly jump into the demo?
It's dealer's choice, but what do you want to do? Do you want to do demo, or you want to talk shop?
Very, very briefly, I'll talk about the code a little bit.
Okay.
So as I said, we trained the code. We trained the model. A model is saved my local as well as in the repo.
Mm-hmm.
And because I'm using my personal work laptop, I'm not using GPU. There's CPU here. That's why I needed to specify it. But you can use, of course, GPU as well. In certain cases, we do that. But here, I have only CPU.
So this is going to load the model. So I guess I have 100 questions, but how long does it take to train the model?
I used, I think, H100 NVIDIA chip. Took less than 20 minutes. 15 minutes and something.
But H100 in the cloud, right? Or do you have an H100 in your laptop?
I wish, no.
Okay. For those who are listening, H100s are very expensive graphics cards.
Excuse me.
Oh, sorry?
Excuse me. I gave you incorrect information.
Oh, sure, yeah.
V100 or A100, either one.
Oh, A100. Okay, so the more affordable but still expensive GPUs. So for those that are listening, it's like H100, A100. There's another letter 100. And I can't remember what they cost. I know maybe like 50,000, 70,000. It depends like when you bought them and what's most popular right now. But the point is that folks, you probably don't own one, but in the cloud, you can rent it for a small period of time. And I don't think it's that expensive. Like it is expensive, but not expensive if you're running it for a limited time, like you said, 20 minutes. Sorry.
Yeah, correct. And I did all the pipeline and model development on a cheaper instance.
Okay.
But when it comes to like inference and model training, special model training and saving the model, that happened in the NVIDIA chip.
Oh, sorry. And now, since this is not a large language model, it's just a model. Was the memory requirements not as insane?
When we use the images itself, we needed more space because each image is bigger than the features that we extracted from MediaPipe. But MediaPipe eventually gives us an array for each hand. Usually there is like one hand in one picture, so it doesn't require a ton of space. But also, I want to remind you, like my data set consists of 7,000 images for each letter. So approximately 7,000 times 26. It's a lot of data.
Okay, so yeah, and I'm just trying to relate this back to LLMs for folks, because the trick with LLMs is that we have to hold the model weights in memory, right? And then they do multiple epochs. And so I think that the neural, like whatever I assume it's deep learning, but like a neural network is going to be way smaller than an LLM. But here you're saying that there's this is true that it might be smaller, but we do have this other issue of loading the images into memory. So that has to be factored in as well. Okay. I think.
Correct.
Right? Sorry, yes.
Yes. Ideally, we did actually this. We phased out the problem. We extracted the images and stored the data somewhere. And then we were done with the images and never looked at the images again.
Oh, okay.
And then worked on those features. Yeah, and again, if you want to like tie it to the LLMs, like there are optimization techniques where you can do pruning or other like knowledge distillation to make it faster. But it's another.
That's beyond my skills.
Okay, here I load because the model was saved, so I'm able to load it.
Mm-hmm. So it was trained prior, and you're just loading it into your machine using CPUs.
Yes, correct. And I am telling model that I'm going to do inference. Don't change anything with the model. This I'm gonna scroll up a little bit. This CV2 from OpenCV is a very well-known image and video library. You may be familiar with it. So I'm going to start the camera with that.
Yeah. For those that are watching, CV stands for computer vision, and I think that is what is responsible for capturing the video and passing it along to media pipeline, I think.
Yes, correct.
Okay.
Oh, okay, let's do this. You're still seeing it, right? It's a very, very common library. It has a lot of features and very easy to learn. I recommend them.
But it's not specific for this. It's a general purpose library for computer vision. And same thing with MediaPipe. It doesn't have to just be for what we're using it for. It's just we're using these two libraries for this use case.
Yes, correct. OpenCV is generally used for many things, including reading an image, digital image, into an array, which is the most common use case.
Okay.
At least everything starts with that.
Okay. I think I've heard the word convolutional neural net. I'm not sure if that's what it is, but it almost sounds like it's one of those 3-letter things.
Convolutional neural network is a type of deep learning model that's used usually for images, sometimes for language processing too, but mostly for images.
I see.
This library has a lot of tools. So when you have a digital picture, for example, you give this method to its location. Hey, this is my image, and it takes that image and converts to an array, bunch of numbers, and therefore you have the representation of that image in numbers. Each number is between 0 to 255 or 254. Here, we're not going to use that. We're just going to use this library to start my camera. And these are the letters that I will be making prediction on. This model, I don't need this at this moment because it uses GPU, but I have the same one with CPU. I'm saying basically, when you have an input data, use my model to make predictions.
I see.
Here, both OpenCV and MediaPipe code is like next to each other. Basically, start my camera and just gather frames from my video. Like take the video, give me the frames. Fast, do it fast. This is what it's doing. And then once I have the frame, this frame is an array. It gives like each frame from this video is converted to an array, bunch of numbers, a list of numbers. This just changes its shape from BGR format to RGB, red, green, blue format. Just changes the place of the numbers. This is a little bit confusing, but basically what's happening here, detect the hands and give me the coordinates of those hands. And finally, once you detect them, you also present them on the camera. And then once you detect the hands, gather that feature, bunch of numbers that represent the hand, feed it to the model. And when you feed it to the model, give me your prediction, basically. Like
Mhm.
model itself is doing it. So it's running right now. So I'm going to share this. I think this one. Here. Do you want to?
Oh, both hands. Okay.
We can do both hands. We can change that to separate hands, but usually use one hand.
If there's two hands,
So the models.
how does that work? Does it compute all of it, or does it separate out the two hands?
Yeah, I have to move it as the interpreter can't see me sign. Okay, so the model is guessing what letters I'm using or where my hands are and things like that. And you could see in the code, the Python, where there was only the first 42 points.
Mhm.
That means it's one hand, right?
Yes.
So that means it ignores the rest. So if I have my other hand here, it'll do the first 42 points. And if you have, what is it, 21? How is it 42? Where's the 42 coming from?
X,
Is that total of two hands?
Y. There's like 21 points. There's X and Y for each point. So therefore, they're like 42. Yes.
Okay, so that's just the X
Oh.
and Y. So that makes 21 and 21. So there's 21X, 21Y. Is that it? You see
Okay.
that? X, it detected it, and Y. See, it's working.
So 42 variables that it has to data points that it has to calculate there. But when you have all 84 up, then what? It just ignores one.
Okay, I think I skipped that part. I didn't do good explanation.
Mm-hmm.
So we have 21 we have 21 points, right?
Vertices, yeah, that have an X and Y value, and if we times it by 2, we get 42.
Yes, each of them actually have 3 X, Y, Z, but we drop the Z. We have X, Y.
Okay.
And then that's actually an array of 221, like 2 columns, 21 rows, or the other way around. But my model takes one array, can't see two-dimensional array. Therefore, I unraveled it and make it one big array. Instead of 2 times 21, I have 1 times 42.
I see.
And back to your question, for the demo purposes here, I said if you see 2 hands, one of them can be different, obviously, or same. Just see the first.
Yeah,
21.
I noticed that the points are colored when you unravel your array. Is like the first cell always the same value, so that way, you know what I'm saying? Like if there's 21 vertices, which has 40, like you have a 40 array of 42, and I see those points are colored. Does it know exactly like this point is always this point, and it'll always appear in the same part of the array when it goes in, so that the model has some level of predictability to predict on based on that array?
I'm not sure if I understand your question.
Yeah. So like if Rob holds his hand up again, and we see the points, right? See how like the thumb is colored white, and it goes, and like this part of the thumb is super white, and then it goes here, it's getting gray, so it's a little bit different. But this point here is white, right? Is this point uniquely identified in MediaPipe, and this is always this variable, like it knows, like this is the thumb?
Yes.
So when you produce that single array, right, is position 0 always the same position in here? So let's say thumb is position 0. Every time it gets fed in for the X value of the tip of the thumb, is it always the same part of the array? I'm trying to understand the predictability of the array for the model. Or could they be in any points in the array? Like they could be in any order they want to.
No, when it unravels it unravels in a certain. You can control how you can unravel it, but once it's unraveled, every single data in the inference and training will be unraveled in the same way.
I see. Okay.
So therefore, consistency. Yeah.
That makes sense. Because I was like, I wonder how the model would handle if all the points are random every time. Must be a really good model. But
So like if you show this, right, like L, this is a good example. It can detect it both ways. But then it's starting to say M, you know, it has a challenge with P, right? It's showing N still. It gets K, but it doesn't show P, even though the same shape, just different orientation. It's upside down. So like K is here, right? But you don't change the shape, you just turn it upside down. So it's something to do with, I think this year it has a hard time with P. Q, it does okay. And so, yeah, we're kind of seeing this go through here with the different letters. U, V, W, X, Y.
Z.
And yeah, so D, L. So see, it gets a little confused there with, yeah, if you want to explain.
Oh, and just a heads up, we have 5 more minutes.
Yeah, I can actually take any questions or if you
Well,
have any.
I think I've answered all my questions. I'm so surprised and like how many variables there are to solve, and it makes it a very interesting problem. I'd love to see this develop further. If you folks end up having more time, I'd love to do a follow-up in the future. But was there anything in particular that really surprised you from the outcome? Like I know Rob has seen these projects many times, these finger spellings. Was there anything that surprised you about going through this process yourself for this project?
What about like 3-point, the D,
What about like the 3 points, the Z, and
Yeah.
or something like what we did with the model? So X, Y coordinates, right? Adding the Z coordinate, that model actually had a really hard time. It failed. It couldn't recognize that. So we ignored the Z portion of things and the model got better. So that was I think that was one thing that was surprising to me. We'd think that, yeah, you would have it enhanced a little bit more, right?
I totally agree that you asked this question earlier. I know there will be a lot of developments in spatial data, especially in this year, maybe next year. But finding this data in American Sign Language letters is going to be an issue, of course. But once we have the spatial data, that Z dimension is going to help us a lot. It's going to solve a lot of problems. Yes, I was surprised to see that Z was total noise for us. But there is actually value there, but we're not there yet.
Okay. And so spatial data is one thing, but how do you feel about the technical certainty of solving this problem, or say trying to get to the next step, which is actually being able to spell out words and detect it? And also, have you seen any in the wild that can actually spell out words and how good they are? I'm just trying to understand, for those that are out there, is this a problem that is close for people to solve, or it's still really hard, or just that general sense? Sorry.
So we've got letters like J and have the movement in them, and they're not static. So capturing those frames before and after, like we talked about, that's something else that I think we want to focus on, and maybe we can try to expand the frames and get more of the frames captured in a series of frames, so that it could detect the language of the letter, or a word, right? So once we feel good about Z and J, those two letters that have movement, once we solve that problem, then we'll be able to add signs into it and gestures and things that we talked about before. So gesture-based, adding those type of things, and then that would just really take off from there, I think. So that's how I feel that we're at right now. But I think it is still a big challenge, and it has been so far.
Cool. Is there any parting words for our boot campers? Excelsior?
Party words, you said?
Oh, yeah, parting words. Yeah, final words for them.
Well, well, there are a lot of opportunities in the fields, and I know they're going to be great if they're going through this Gen AI bootcamp. They are going to realize there will be a lot of applications out there, and I wish good luck to them.
Great. And Rob, any words for from yourself there?
Sure, yeah, something to add just for all of you out there. If this is your first attempt and you fail, trust me, you will. Just keep going. Don't get discouraged. Just try it, iterate, walk away, think about it, come back, work on it. And so it's all a process. You will get little wins along the way. And so just doing that, being able to keep at it, it might take 2.5 years, it might take 2 days, who knows, right? But you will get there at some point. So just keep working at it. And that's really the whole point of all of this exercise, right? It's we don't know what we're going to get out of it. And, 2 years or 2 months from now. So that's what I always like to remind folks is that you might get up in the morning and get all, some added unexpected motivation. So yeah, just keep at it.
Great. Well, I appreciate both your time here. We are out of time, but I'm going to see all the boot campers here in class soon. And yeah, again, just appreciate you taking the time and letting me ask so many technical questions. But yeah, we'll just say goodbye here. Ciao, ciao.
Thank you. Thank you.
Thanks.